Hello everyone. I want to thank you all for attending our first Student Math Talks night for Dearborn's Math Club. My presentation is titled Cellular Automata, Complexity from Simple Dynamics. To start off, cellular automata are collections of colored cells whose states evolve over time based on a set of rules in relation to the value of the neighboring cells. They are a specific variety of dynamical system, one that is best described as deterministic, discrete valued, and existing in discrete time. The study of cellular automata began in the 1940s by Stanislaw Ulam and John von Neumann, two mathematicians who partook in work on the Manhattan Project. They wanted to explore the possibilities of self-reproduction in machines, a notion that was widely challenged at the time. This was a development within the emerging field of cybernetics, a larger effort which included Norbert Wiener to study control systems which mimic biological processes. As we'll explore later in the presentation, von Neumann proved to be quite successful in describing structures within cellular automata that are capable of much more than just self-reproduction. This field has been the subject of research from both amateur and professional mathematicians alike. In terms of applications to other fields, a lot of work has been done in using CAs to simulate population dynamics, develop CA-based algorithms for random number generation, procedural generation, image filtering, distributed computing, and structural repair, the lattermost we'll be looking at the end of this presentation. And a quick note before we continue, despite the fact that cellular automata can exist in any dimension, this presentation will only be looking at those in 1 and 2 dimensions. Here's an example of a one-dimensional cellular automaton, with the initial state shown to the right. The cells have two states, white or black, implying that this CA is binary valued. We'll base the transformation of one cell on the values of itself and its two nearest neighbors. To the left is a table of rules that will determine the middle cell's state at the next generation. As time progresses, the subsequent generations are drawn below each other. Note that the rules for the cells at the end of the lattice are based on the other endpoint, so one can think of the left neighbor for the first cell as the last cell, and vice versa. Here's a picture of the cellular automaton at time 1. Notice how the 2nd, 5th, 9th, and 11th cells have turned dark. We can continue with this pattern for the 3rd, 4th, and further generations. Now, while this may seem simple, the real interest in cellular automata comes from the fact that rule sets can produce unexpected complex behavior as time goes on. If we were to let this system evolve over a large amount of generations, we would get a picture that looks like this. Notice how these patterns are not necessarily random, but also don't follow a neat flow. From visual inspection, it looks like our automaton has produced branches of triangles against a backdrop. Certain CAs like this are said to occupy a space on the edge of chaos. Many rule sets that produce interesting behavior like this have been cataloged. This rule set is known as Rule 110. We'll talk about why it's called Rule 110 very shortly. To give you some more recent history, this is Stephen Wolfram, a British-American physicist and computer scientist. He has become a face very closely associated with cellular automata. For a quick biography, at the age of 17, he wrote a paper in the field of quantum chromodynamics. This paper attracted the attention of Mary Gell-Mann, who was a Nobel Prize-winning physicist. Gell-Mann invited him to join his research group and pursue graduate studies at Caltech. Wolfram ended up applying to the university and finished his PhD in 2 years. Following this, he conducted research into cellular automata for 2 decades and published his findings in a 1,200-page book titled A New Kind of Science. In this book, Wolfram classifies all elementary cellular automata into 4 categories based on their limiting behavior. Class 1 contains those which eventually stabilize and stop changing after some period of time. Class 2 contains those which exhibit oscillatory behavior where each cell changes in a well-defined pattern. Class 3 consists of automata for which behavior remains completely unpredictable and random. Class 4 consists of automata like Rule 110, which generate complex structures over their evolution. The big idea that Wolfram tries to put across in this book is that all phenomena in nature is just the universe performing a computation, and that very simple processes such as Rule 110 can simulate all of these sub-computations. While this idea has generated a lot of controversy in the scientific community, we're going to explore why he believes this later on. Here are some examples of cellular automata that exist in each of our 4 categories. Rule 232 corresponds to our stable class, since the cells stop changing states after a few time steps. Rule 1 corresponds to our oscillatory class. Rule 90 corresponds to our chaotic class, and Rule 110 exists in our complex class, as we saw before. Before we go any further, we're going to introduce the formal notion of a cellular automaton. We define a standard cellular automaton as a 4-tuple. The first element of this 4-tuple is the lattice or grid of cells that the state of our cellular automaton will exist on at a given time point. Lattices are a finite grid of cells, and hence they are isomorphic to the direct sum of Z mod n. The second element defines the initial state at time 0 before any change has occurred. The third element is our transition function, which includes a neighborhood size and the list of rules for each possible neighborhood configuration. Like we saw in Rule 110, these transition functions are commonly defined using a table of rules, but they don't necessarily have to be. We can define the transition function in any manner as long as we consider all possible local configurations that a group of cells could take on. Finally, the fourth element refers to the configuration at a particular time point in the evolution of our automaton. As a quick remark, in our first example, we were on a one-dimensional lattice that had 11 cells, which means that our lattice was isomorphic to Z11, and our initial state was given by a binary index set. As was mentioned previously, Wolfram categorized all elementary cellular automata into 4 categories. By elementary, we mean cellular automata that have a neighborhood radius of 1 and binary state values. Since we include the middle cell itself, a neighborhood radius of 1 gives us a total neighborhood of 3 cells. Suppose we wanted to compute the total amount of distinct elementary cellular automata. There are 8 unique permutations of 3 cells, and we can associate a binary number with each of the permutations to describe an update rule. In total, this means we have 2 to the 8, or 256 total distinct rule sets of elementary cellular automata. Naturally, we can also assign each of them a number by converting their binary representations in the rule table to a decimal number. We call this number a Wolfram code, and the Wolfram code for a particular ECA can range from 1 to 256. Here's an example of the computation of a Wolfram code for Rule 110. The 7 groups of 3 adjacent cells to the right are the binary representations of place values for 1 through 7. If we want to convert this to a decimal number, we simply multiply them by their corresponding coefficients and add them up. As a remark, it's important to note that all Wolfram codes are unique by the basis representation theorem, so we can never get 2 distinct rule sets which compute the same code. It is possible to extend this idea past binary states in the neighborhood of 2, but the total amount of unique rule sets becomes large rather quickly. Let's now shift gears and move to a more famous result in cellular automata. In the 1960s, the late mathematician John Conway began doing experiments with cellular automata to determine if von Neumann's original prediction about machines capable of reproduction could be extended. Instead of just focusing on a set of rules that would recreate multiple copies of a single configuration, he wanted to build a rule set that simulated simple population dynamics with the hope that cells would reproduce in some form autonomously. It is the population dynamics that come from this cellular automata that gives it the name game of life. Conway followed 4 principles when he was constructing his rules. Number 1, there should be no explosive growth. Number 2, there should exist small initial patterns that produce unpredictable outcomes. Number 3, there should be the potential for von Neumann universal constructors. We will get into what these are later on. Number 4, these rules should be as simple as possible while adhering to the above constraints. Through trial and error, a rule set was found that produces conditions under which a simple population model can be simulated. First, the game of life is defined to exist on a 2-dimensional binary lattice where a dead cell is white and an alive cell is black. The size of the lattice is arbitrary. Conway chose a 2-dimensional lattice because population dynamics are not intuitive in 1 dimension. There are 4 rules in the rule set. Each of these rules represents a process that occurs in a natural ecosystem. The first is death by underpopulation, where any living cell with fewer than 2 living neighbors dies. The second is persistence, where any living cell with 2 or 3 living neighbors continues on to the next generation. The third is death by overpopulation, where any living cell with more than 3 living neighbors dies. The fourth is emergence by reproduction, where any dead cell with exactly 3 living neighbors becomes a living cell. In this example, we have the evolution of a random initial configuration in the game of life. Notice that we have a variety of structures which emerge as time goes on. In the corners, we have clusters of stable cells as well as oscillating groups of cells in a line. If we allow this cellular automaton to continue, it will eventually stabilize to this configuration. Once stabilization is reached, we can think of the amount of living cells as the carrying capacity of the system, similar to the carrying capacity of a system modeled by a logistic curve. Certain initial configurations also yield more interesting structures. The one shown here is called Gosper's glider guns, which has the namesake of its creator, Bill Gosper. This cellular automaton oscillates in state indefinitely and emits structures that are traditionally called spaceships on the diagonal. This glider gun construction proved to be significant for several reasons, most notably as an example that a finite amount of cells can be used to create an infinite number of cells. One can think of the production of spaceships as an elementary form of reproduction. Going further, other people have expanded on the rule set in the game of life. A notable one is Biles loop, a cellular automaton with 6 possible states. This functions similar to how bacteria may expand exponentially. Under this environment, clusters of cells are capable of producing exact copies of one another. This is a prime example of von Neumann's prediction that cellular automata are capable of reproduction. So, let's backtrack for a moment and begin looking in detail at some of the things we mentioned in previous slides. When introducing the game of life, we noted that the third principle Conway followed when deciding on his rules was the possibility of von Neumann universal constructors. We can define a universal constructor as a pattern within a cellular automaton which has the capability of constructing any other type of configuration, provided it can read a description of the pattern encoded in an instruction set. This is a digital implementation of von Neumann's 29-state universal constructor in a cellular automaton which is not the game of life. This particular implementation contains 4 components: an input stream at the top left, the output arm in the bottom left, a memory tape at the bottom right which stores the input containing the description of the pattern to be built, and the data readout at the top right which provides a binary representation of the cells being output. An important emphasis to make here is that there exists no sort of central control for this machine. This entire constructor operates off of a local rule set. In 2004, John Conway published a proof that a pattern for the universal constructor exists in the game of life. As of October 2020, it has still not been found. As a related result, Matthew Cook, who was an assistant to Stephen Wolfram, proved that the first rule we looked at, Rule 110, is Turing complete in 2004. For a definition, we call a system Turing complete if it's capable of simulating any computable function. Almost everything we can think of in mathematics is considered computable. In layman's terms, if we can prove that there exists an algorithm to perform some task representable as a function, then our task is considered a computable function. As one may conjecture, the existence of a universal constructor within a system implies that the system is Turing complete. In theory, we should be able to build configurations within the game of life in Rule 110, which can perform any computation and represent it in some capacity. The challenge of programming these cellular automata is to find a configuration which represents our data well and is guaranteed to evolve to a state representative of a desired output. As one may guess, this is not an easy thing to do. That being said, we shouldn't abandon the idea of using cellular automata as computers. Instead of looking at how to program a specific cellular automaton that is known to be Turing complete, Another approach would be to find transition functions that are capable of simulating a computation on a wide variety of inputs. While these transition functions may not necessarily be Turing complete, them being able to perform a specific computation well on many inputs is really what we're interested in. Let's try to make a transition function that will simulate a simple computer program. Consider the following problem of a one-dimensional cellular automaton taking in a row of cells as an initial configuration and outputting what color represents the majority. This is called the density problem. Here's an illustrated example of what we want to do. We'll define the input as the initial configuration, the output as the state of the cells at a predetermined time step k, and all in-between steps as the computation in progress. This problem, and another, called the synchronization problem, was explored in depth by Melanie Mitchell and her collaborators at the Santa Fe Institute. Most of the following information comes directly from their research papers that I've cited at the end of this presentation. One thing we know is that out of all the cataloged elementary cellular automata, none of them exhibit behavior like this. For this reason, we're going to increase the neighborhood radius in our transition function by 2, and now try to use the nearest 3 neighbors to define our rules. The reason we do this is that computer simulations suggest that increasing the neighborhood radius by just 1 is still not large enough to produce our desired behavior. When thinking of ways we could construct our transition function, one heuristic we could employ is local majority voting. It yields a simple rule set, and its ability to succeed sounds plausible, since the local behavior would mimic our desired global behavior. To do this, we just explicitly define our transition function as an ordered list of rules, the first half mapping to the white cells, the second half mapping to the black cells. However, if we try to do this, we get a result that looks something like this in practically all initial configurations. As you can see, this state stabilizes and does not give us the result we want. Now, we can try variations on this transition function or attempt to search for it by means of a list or tree, but even with just a radius of 3, we already have an intractable amount of rules to search through. So, if direct programming and classical searching algorithms are out of the question, what do? One approach we could consider is in using a non-classical searching algorithm. As we'll see, a class of randomized techniques called genetic algorithms have shown promise. As an overview, they work so well since they can mix and match rules across several generations in order to come up with a cellular automaton that conforms to our desired behavior. The next 2 slides involve some definitions, and we have a lot to unpack. Don't worry if you don't immediately catch everything the first time. We'll be going over an example afterwards. A genetic algorithm is a biologically inspired meta-heuristic used to generate high-quality sets of elements called populations over the course of several iterations. We'll start with an initial population that contains a finite amount of k-digit strings and define a fitness function to map each of these strings to a real number. Our goal will be to construct a new generation of elements, p of n plus 1 from p of n, whose elements on average have a higher total fitness than the previous generation. In the next slide, we'll get into the details of a genetic algorithm, but a word of warning for notation. Plus does not represent addition between our elements. It represents string concatenation and is a non-commutative operation. We'll also define another function t as the truncation of a string from one of its ends. S represents the string we'll be truncating, x represents the amount of symbols we'll be keeping after truncation, and y is a binary value which represents the end of the string we'll be cutting from. Consider the string a. X is 2, so we'll be keeping 2 of the 3 symbols, and we'll also be cutting starting from the left end. This means our new string following this operation is O1. Likewise, consider b. X is 3 and y is 1, so we'll be keeping the 3 symbols 4, 8, 5, starting from the right end. So this slide details the broken down process behind a genetic algorithm. First, we will define an index collection of t-sets, with all but the first being empty. The first set will contain a finite amount of k-digit strings. In the case of our density problem, any reasonably sized amount between 50 to 200 should work just fine. In her paper, Mitchell uses 100. Next, we will define some fitness function f of p, which maps from the strings in a set contained in p to the real numbers. Thirdly, we will perform the following process iteratively for each generation leading up to the last. First, for each k-digit string in the current generation, we will compute the fitness coefficient. Next, we'll select with replacement the same amount of ordered pairs of strings from the population as there are elements in the total population. So, if we have 100 elements in a population, we'll select 100 pairs of those elements. The probability of an element being chosen is equivalent to their normalized fitness coefficient. We call this genetic selection. Next, for each ordered pair that we chose, we'll select an integer q between 1 and the length of our strings minus 1. This represents a crossover point. We'll take the first part of p0 up to the qth digit and all of p1 after the qth digit and concatenate them. The concatenation of these two strings will give us another k-digit string. Finally, we will take this string and allow a process called mutation to occur. Mutation is an event that a given set of bits will flip with small probability. This is included in our process because mutations can provide beneficial traits to a string with respect to the fitness function that would otherwise not occur with crossover. Since we want mutations to occur infrequently, the probability of a single symbol mutating is usually set to a small number, like 5 or 10%. And that's it. We allow this process to take place iteratively across every generation up to t-1, and we'll be left with a population t which should have a much higher aggregate score with respect to our fitness function. So, I promised an example of our genetic algorithm in action, and here it is. Suppose that we have an initial population and we want to observe one round of evolution. For simplicity, let our initial population be 4 8-bit strings and our fitness function be the amount of ones in a given string. The higher the number of ones, the better fit the string is. Here, we have computed their fitness coefficients as 3, 6, 4, and 3. In total, our aggregate fitness for the set is 16. Since we want to select the fittest strings for crossover, we can compute the probabilities of being selected by dividing their fitness coefficients by the aggregate fitness of the set. Now, since we have 4 strings in generation 0, we will want to select 4 ordered pairs to create 4 strings for generation 1. Next, we'll want to select 4 integers between 1 and 7 to act as crossover points. In this example, we'll use 2, 5, 4, and 4 for our pairs. Now we can begin constructing the elements of P1. For our first element, we'll take the first 2 numbers from P2 and concatenate it to the last 6 numbers of P3. Finally, we'll mutate the digits in the string. We can do this with the remaining 3 pairs to get the elements of generation 1. If we tally up the aggregate fitness of this set, we get a total of 18, 2 more than our previous generation. If we do this for several more iterations, we would get a population that has a much higher average fitness than what we started with. Now that we've seen genetic algorithms in action, we can apply them to our density problem. We'll do this in 3 parts. First, we'll create a collection of random cellular automata rule sets represented by strings. Next, we'll compute fitness coefficients for the rule sets in each generation. Finally, we'll perform selection, crossover, and mutation to construct the next generation of rule sets. To handle the first step, we first have to figure out how to encode rule sets as strings. To recall, we selected a neighborhood radius of 3 to work with since it provided the necessary bit length for a genetic algorithm to solve this problem. Similar to how we computed Wolfram codes for elementary cellular automata, the key idea to encoding these rule sets in the form of strings is by viewing each individual rule in the rule set as a place value in a binary string, and the resultant cell of that rule as the digit in that place value. For example, consider the picture to the left. The first rule concerns the cell configuration of our central white cell surrounded by white cells. If we regard white cells as zeros and black cells as ones, our first configuration represents 0, which corresponds to the first place value in a string. The digit in the first place value is 0, since our resultant cell is white. Going further, the second configuration corresponds to the second place value, which also has a value of 0, and so on. In this manner, a rule set can be represented as an 128-bit string, since we have 128, or 2 to the 7th power rules in a rule set. So, all we have to do for our initial population is generate some amount of random 128-bit strings, and each of those strings will represent a rule set. Our picture is the first rule that we generated broken down. The last thing we have to do before we can apply a genetic algorithm is construct a fitness function to rank our rule sets. Since we're randomly generating bit strings anyways, an easy thing for us to do is to take a sample average of how well the rule set does when applied to a large number of random initial configurations. As we've defined computation in a cellular automaton previously, we'll consider the initial configuration to be our input and a certain generation k to be our output. If for some randomly generated initial configuration, we have the desired configuration after applying our transition function k times, we'll consider the rule set to have correctly classified the density of that configuration. Formally, we'll represent our fitness function as the sum of initial configurations which resulted in the correct cell configuration at generation k over the total amount of initial configurations fed to the rule set. For a notational clarification, that Blackboard 1 is called the indicator function. It returns 1 if the condition inside of the brackets is true, otherwise 0. So, now that we've represented our rule sets as a population of strings and have defined a fitness function, we can evolve our strings just as we did with the first example. So, after iterating for several generations, we'll have a collection of CA rules which have high fitness under our evaluation function. Here's a picture of one rule set which had high fitness. Notice that it generates the correct result for a majority black configuration. While only one result is pictured here, it has the correct output for most of the initial configurations, both majority white and black. So to recap, through genetic algorithms we've found a rule set that functions as a highly specific computer. As we've mentioned before, it also has been shown that we can generate other rule sets which have behavior outside of density classification, such as the synchronization problem mentioned in Mitchell's paper. When studying cellular automata and other decentralized systems, a more general question arises. How do decentralized systems, whether they be mathematical or natural, generate a mechanism such that they can accomplish global behavior without centralized control? While there's no known answer to that question, in the case of our density problem, Mitchell and her team found that cellular automata were modeled well by something called a system of particles and regular domains. While I won't dwell on this explanation for the sake of time, I will give a high-level overview of the conclusions they came to. Consider the image to the left. This is the cellular automata we saw in the previous slide with all of the regular patterns filtered out, only the boundaries now being visible. It's thought that these boundaries carry information that can change the state of a regular domain within a region when they collide. These boundaries are called particles because just like two particles in physics can collide to produce a different particle, the boundaries interact with one another and create new domains with different properties which can carry information about regular domains. For an example, consider the collision between the delta and gamma particles to the left. While these particles surround a regular domain of white cells, they collide and produce an eta particle which bounds a regular domain of black cells, the last line of which acts as the desired output of the automaton. Other theory and empirical evidence backs this idea up, so it's thought that when our genetic algorithm is processing populations of rule sets, the rule sets are really learning that a system of particles is an effective way to perform computation. If one thinks of this as a simplified model of the particles that are so central to physics, Wolfram's opinion that our universe is really just a giant decentralized computer may not seem like that much of a stretch. So I'll end here about cellular automata as a model of computation. One last thing I want to mention before this presentation ends is that CAs can serve as good models for a variety of complex processes. Back in February, a collaboration between researchers at Google and Tufts University were able to combine the usage of neural networks in cellular automata to produce a system of cells that is capable of automatically repairing itself without centralized control. Consider these cells in the shape of a lizard. While locally they have no concept that they're in the pattern of a lizard, if I damage the configuration, they're capable of regenerating automatically, among having other functions that are akin to cells in biological organisms. This research is thought to have applications in understanding the relationship between simple cells and the very complex neural network that is the human brain, among other things. In the references within the description, I provided a link to a website where you can read this paper and play with the simulation they have made yourself. So that's all for my presentation. Thank you for listening.